All right, so this is what we're going to be doing from now on. I'll be sending you these videos, and through these videos, you'll watch them, and then we'll return in class and discuss what was in the videos that I sent. So we're going to do things the exact same way as we did them before. Starting off, this is obviously still Introduction to Statistics. That has not changed. And we are still talking about inferential statistics. So, in our conversation about inferential statistics, we previously talked about probability and we talked about normal distribution. So, today we're going to talk about sampling distributions and population parameters. So, where are we basically in this class? This is like this is where we are. So, we've already collected data, we've organized and presented the data. And the question is still that we're answering is still now what? Now what do we do? So the answer after that is we do inferential statistics. And basically the inferential statistics allows us to find more information out about our populations. So going back to our analogy with going back to our analogy with what I'm trying to say, going back to our analogy with our soup, right? When we do our inferential statistics, we've taken out our spoon of soup. That's what we did in the beginning, which is basically covering our sampling. That was our sampling methods and how we actually go about taking our sample. Next, we described it, right? The description was basically our descriptive statistics, right? We had to do all the measures of center, all the measures of variation. We had to do all the little charts and all of the histograms and graphs and all of that. And now, basically, what we need to do is use all of that information we found before to do our inferential statistics. And the key thing is what? The inferential statistics is going to tell us about the rest of the pot. That's what our inferential statistics is going to do. It's going to tell us, right, about the rest of the pot. And that's kind of the key here. We want to learn more about the rest of the pot. So, hold on. There we go. Back to our marker. Uh-oh. So, I keep messing up and writing something by accident. Okay. So when we are discussing um, data, any kind of data, wherever we're doing statistics, in general, our goal, right, is to learn information about a population. Or basically, in short, our goal is to find out population parameters. That's our goal. Anytime we do any kind of statistics, is to find out population parameters, right? And most times, right, it's almost impossible to do a census, right? To get information about a complete population. It's almost impossible most times. So what we do instead is we collect sample statistics. Remember, statistics are what? Statistics are information about a sample, right? And those sample statistics serve as point estimates, right, for the unknown population parameters. So let's say, for example, we were playing a game of darts, right? So I'll draw my bullseye right there in the middle, and I'll draw some rings going around the outside. Let's say when we play this game of darts, and don't laugh at my drawing of a dart game, right? Don't laugh at my dart game drawing. But when we play this game of darts, every time we take a sample, right, with like throwing a dart at the board. Every time we take a sample, we throw a dart, throw a dart, throw a dart, throw a dart, right? That's what we do when we take a sample. We're like throwing, just lobbing darts in at the board. Now, here's the thing. When we throw those darts at the board, we're aiming right at the center. That's what we're aiming at, right? And all of those darts, they may not be exact because maybe we're not the best dart players, but all of those darts are aimed at the center. So imagine if there was somebody else sitting on the side, right? If there was somebody else sitting on the side and that person who's sitting on the side was watching us play darts, do you think that person, based on where our darts, let's say they couldn't see the board, all they could see was where our darts hit. Do you think this person, a little question mark, do you think this person could tell, right, where the center of the board was just by looking at where our different darts hit, right? Could the person tell? Now, obviously, if we were a really, really accurate dart player, then it'd be really easy to tell, right? So if I had a bunch of darts like this, right, it'd be kind of easy to tell where the center of the board was. Obviously, the center must be somewhere over here because that's where all the darts are kind of clustered around. All the darts are kind of clustered around that point there, right? If we weren't a good dart player, it might not be so easy. But when we do statistics and we collect data, if we collect data well, right? If we do our samples properly, right, and we account for bias, we take large enough samples and all of that, then that's basically the equivalent of being a really good statistical dart player, right? And if you're a really good statistical dart player, somebody else will be able to look at where you threw darts and be able to tell where the bullseye was. The bullseye, right? The bullseye is what we're aiming for. That's the parameter, the population parameter. And our sample statistics, which is our attempts at throwing the darts, those are basically point estimates for that bullseye or the parameter. And when we say point estimates, we mean that they point us in the direction of the bullseye, right? But they don't tell us exactly where the bullseye is. Now, I know that analogy is kind of odd, but that's like the best way to think of it. Think about watching someone play darts, but you can't see the dartboard. Could you tell where they were trying to aim? Could you say, okay, this is the bullseye based on where they hit on the board? Right? Now, when we do sampling statistics, when we take statistics from samples, right? Every time we take a sample, if we just did the same population and we just took a bunch of samples out of that population, every time we took a sample, right, each of those statistics would vary from one sample to the next sample. They wouldn't all be the same, right? And when we do those sampling statistics, right, we get basically what's called a margin of error. And that margin of error is basically what is telling us how accurate our point estimate will be. That's what's telling us how accurate our point estimate will be. And again, the idea is that when we take a bunch of statistics, when we take a bunch of samples and we find information about all those samples, they are leading us closer and closer to the population parameter. And that's basically where we are trying to get, right? Now, we're not going to go all the way into finding a margin of errors yet, right? But the first thing what we want to do is we want to find out about the point estimates and why they are different when we take different samples. Why is it that if I was to take 10 different classes at Trinity and I found the average height or the mean height of each of the classes, all of those mean heights would be slightly different. And actually, we have a sample here, an example here. So let's look at this example right down here. So in this example, what we're doing is we're taking a random sample of 1,000 adults from each state, right? How many states are there? There are 50 states. And we're taking 1,000 adults from each state. So 1,000 from, that's key, from each state, right? So in total, we'll have what? 50 times 1,000. 50 times 1,000 is what? 500,000? Yeah, I think it's 500,000. Did I just add it? No, I'm sorry. A slow moment from a math teacher is 50,000. Sorry, slow moment. So we're taking 1,000 from each state, and that's a total of 50 50,000 people that we're sampling. But again, we're going to treat each state as its own sample. So those 1,000 adults from each state, each of those groups of 1,000 will be their own sample. So the question is, if we found the mean of each state, right, would you expect, right, that their heights, the mean heights of each individual state would be the same, or would they be somewhat different, like just a little different, or would they be very different? So what I want you to do is I want you to pause the video and come back in a second. Like, think about it for a second and then come back and see if your answer is correct. All right, so that's the question. We take those 1,000 adults from each state. So we have 50,000 or 50 different samples. So we have a sample for DC. Well, DC is not a state, but I'm going to count it in there because DC should be a state. We have a sample from Maryland, a sample from VA, a sample from New York, sample from California, sample from I don't know, Texas. I think Texas is what, TX, right? Samples from every single state. ... The question again is, will each of those states have the same mean height, somewhat different mean height, or a very different mean height? And the answer was basically that they won't be the same, but they'll be somewhat different, right? Only somewhat different. That's key. Only somewhat different. So they're not going to be very different. You're not going to take one state and find that one state has a mean height of 7 feet 2 inches versus another state that has a mean height of 4 feet 1 inch, right? You're not going to find that because everyone's going to kind of, yes, okay, you may have tall basketball players somewhere, right? Or really, really short people in some places, but they'll all kind of balance out to kind of put us in some place, right? In the middle. That's what's going to happen. They're all going to balance out. Now, this process that we just did, where we took a bunch of different samples and we're comparing the means of all of those different samples, this process is called creating, right, a sampling distribution. That's the process. We took a whole bunch of samples and we're looking at the descriptive statistics of each of those samples. We're not looking at one sample, which is what we've been doing up till now. Up till now, we've been taking one sample. Here, what we're doing is we're taking a bunch of different samples, more than one sample, 50 samples, 100 samples, right? As many samples as we can. And we're comparing the descriptive statistics about each of those samples. That's what we're doing, comparing those descriptive statistics. So we may compare, right, the means. We could even compare the medians. We could compare, what else could we compare? We could compare proportions. So the proportions might be like probabilities, that kind of thing, similar to like what we just did in the last assignment. We could compare the standard deviations. Excuse my spelling. We could compare the standard deviations. What else could we compare? A couple other things that we could compare. Let me see what else I want to put in there that we could compare. We could compare the variances, which again are related to the standard deviations. So we could compare the variances, right? And we could be comparing all of these for each of the samples that we take, right? So let's say sample 1 had some numbers, and then sample 2 had some numbers, and then sample 3 had some numbers. We could compare all of them, right? For each of them, we can compare those values for each of the things that we have. So moving on, let's look at what happens when we look at the proportions of a bunch of different samples. Now, when we look at the proportions, that's the exact same thing as what you had to do in the assignment, right? When you had to do the homework assignment when we looked at COVID-19. When you had to do that assignment, what did you have to do? You had to take the data and you had to compare the different proportions. You looked at a couple of different proportions. The proportions are basically probabilities, like what percent of the people did this and what percent of the people did that, what percent of the people recovered, etc. Right? Those are the proportions, and we compared the proportions. And what you should have created was something like this, where basically you can have a distribution of all of those proportions. So when you did that assignment, you had proportions you got for China, proportions you got for Italy, right? Spain, US. I'm going to say ... because you had to do the top 10. And each of these would have had a p hat, a p hat, a p hat, a p hat. What we'll do is we'll put a little 1 next to that one, a little 2 next to that one, a little 3 next to that one, and a little 4 next to that one, and say ... Right? So instead of looking at one place, which would be just looking at, say, China, right? We're looking at all of the different places, and then that becomes like our new layer of data. That's what that becomes, our new layer of data, right? That's what that becomes. So when we do this for proportions, right, what we find is that when we take all our samples and we find proportions for each sample, what we find is that when we put them in a distribution, we make a histogram and we see what the shape of the distribution, we find that the proportions tend to be normal, right? They tend to have a normal distribution when we do that. That's what we find, right? That the proportions are normal. And that's very important. That's a very important observation because as we already saw, there's special things. Last class, we talked about it. There's special things we can do when we have a normal distribution. So again, what we would be doing, right, is we would be taking all of these, P1, P2, P3, P4, and we'd be plotting these numbers out to get a histogram, right, and a distribution. So it would be like all the different numbers, like the P1, P2, P3, P4, so on and so forth, for all of the different things that we found, for all of the different samples that we took, because that's basically what we did in the homework assignment, right? We took a bunch of data and we treated each country as if it was its own sample, and then we compared the values that we got for each of those samples, right? We compared the proportions we got for each of those samples. Now, just a little note, how we say this. So you may have looked at that and said, what are we supposed to say here? So when we have this little triangle on top of it, we call that a hat. So the way we say this is literally P hat, right? That's what we say. That's how we say that, P hat. Now, another note, P hat, right? That is a statistic. P hat is a statistic. If we wanted the population, we take off the hat. So if we want the population, we take off the hat and we just have P. So the population proportion is just P. The sample proportion is P hat. Now, it looks almost like the same slide, but I promise you it's not the same slide because this time we're looking at means. So first slide, we're looking at proportions. This slide, we're looking at means. So again, this is like our example with the heights. We took 50 different samples, and for each sample, you found a mean. You found a mean, you found a mean for every single sample, right? And when you find those means, what do? You get X1, you get X2, X3, so on and so forth, right? X1 would be the mean of your first sample. X2 would be the mean of your second sample, right? Or X bar 1, I'm sorry, I'm saying X. X bar 1, all right, X bar 2. So let me show you an example of exactly kind of another depiction of what we mean. So if we look over here, let's say this blob represented our population, our entire population. what we would be doing is basically we cut this section out, right? This would be our first sample. And then we say, okay, let's do another sample. We cut another section out. That's our second sample. And we cut another sample out. That's our third sample. Let's say we kept doing that and kept doing it and doing it and doing it and doing it, right? If we kept doing that, for this one, we would have a mean for sample 1. So we'd have x1 bar. Sample 2, we'd have x2 bar. Sample 3, we'd have x3 bar, right? So for each of our samples, we would get an x bar for each one. And let's say we kept doing it and doing it. We kept doing it, and we didn't stop doing it, right? Basically, that's what would allow us to build this, where now we have a distribution of all of the sample means. And we get another important note. When we do a distribution of sample means, when we look at a bunch of different samples and we look at their means, they tend to be normally distributed as well, right? Just like our sample population, our sample proportions, right? They tend to be normally distributed. And you should already know it, but just as a reminder, X bar is a what? Statistic. Mu is a what? Parameter. Right, so that's mu and X bar. One is a statistic, one is a parameter, but they both are the mean. Now, with the means, I think it's a little easier because we work with the means a lot. The sample means estimate the population mean, right? All of our sample means estimate the population mean. So a way of thinking about it is if we took a whole bunch of different sample means and we found the average of all of those different sample means, right? We took a whole bunch of different samples, and then we found the average of all of those different sample means. We found the mean of each sample, then we found the average of all of those different sample means. What we would end up with is a number that was almost exactly or really, really close to our population parameter. That's what we would end up with, right? A number that was really, really close to that population parameter. Now, when we look at the variances, again, the variance is what? The variance is the standard deviation squared. So the variance, again, that's our standard deviation squared. Right? That's why it's just S squared, our standard deviation squared. Now, when we look at our variances, we're doing the same thing. We're taking our sample 1, sample 2. Same thing we did here when we took all of our different samples, right? Same thing we did here. We took all of our different samples. When we did that, right, we found the mean of each one. We found some proportions for each sample. What we're doing now is finding the variance for each sample, or the standard deviation for each sample. And what we find is that when we do that for all the variances and we try to make a distribution of all of the variances, we tend to end up with a skewed distribution, right? That's what we tend to end up with. We tend to end up with a skewed distribution, right? And that's another important fact, because there was stuff we could do for a normal distribution, but we didn't have something yet that we could do when we had a skewed distribution, right? Now, again, another note, we're looking at S squared versus sigma squared. Statistic, parameter, right? Statistic, and that is a parameter. Did I spell it right? Yeah, parameter, right? So again, we're trying to take our statistics and use them to estimate our parameters, right? And to get the best estimate, we try it over and over and over again, and we average those things out to get our best estimate. Now, what we call a sampling distribution. It's like what we just talked about, but there is a very particular distinction there. When we have a sampling distribution, we need to take all possible samples, right? That's the important part. All possible samples of the same size, right? All possible samples. So that means if we had, say, 1,000, right, Trinity students, and that's what we were looking at, Trinity students. And let's say we were doing sample sizes of 30 students, sample size of 30 students, we would not create a sampling distribution until we had taken samples of 30 students all the way to the point where we had taken all of the possible samples that we could take, right? Meaning there are no possible samples left that we can take. All of the ways of mixing it all around, right? All of the different ways of mixing it all around, we've done it all. And I mean, you all know how to find how many possible ways we could take 30 students out of 1,000 students, or at least you should know. We've gone over it, right? So if we were to draw lines out, for our first, we just do some multiplication. Our first student, right, we would have a choice of 1,000 students to pick from. Our second student, we would have a choice of 999 students. Third student, 997 students, and we'd multiply that out all the way till we got to 970 students. So it'd be a really, really big number of possible samples that we could take out of 1,000 Trinity students, right? But when we do that, right, that's what we create. We create what's called, a sampling distribution, right? We create a sampling distribution, and that, again, is a particular thing. Now, when we take a couple of samples out, a sampling distribution is when we take all of the possible samples, right? All of the possible samples. And when we have that sampling distribution, we'll make a histogram, right? Or we'll have some kind of formula or a table to represent it. So there are different ways we can represent that sampling distribution. But that's where we take all of the possible samples, and for each sample, we find some statistic about it, right? And then we have a sampling distribution. Now, we already talked about estimators, but again, an estimator is basically just something that lets us infer the value of a population parameter, which again is the goal of statistics, right? That's what an estimator is. When we have what's called an unbiased estimator is basically when the statistic targets the value of the corresponding population parameter, right? And basically that means that the mean of the sampling distribution is equivalent to the population parameter. So for example, if we were to take a whole bunch of means, so take a whole bunch of samples, sample 1, we find the mean of it, that gives us x1. Sample 2, we find the mean of it, that gives us x2. Sample 3, we find the mean of it, that gives us x3. X bar 3, I'm sorry. Sample 4, we find the mean of it, that gives us x bar 4. Sample 5, we find the mean of it, that gives us x bar 5, ... Now, when I find the average of all of these, right? When I find the average of all of these, we're going ... Let me actually write it all the way out to what we're going to. So this will help. We're going ... and we're going to go all the way up to our nth sample. Right? We're going all the way up to xn. Again, n is just a counting number. That's all n is. Right? Just saying we don't know how far we're going, but we're going all the way up to xn. Now, when I find the average, so I'm going to write it mathematically, and I'm going to write it like with words. So if I find the average, right, value of x bar, right? That's what I'm looking for, the average value of x bar. So I'm going to add up x bar 1 plus x bar 2 plus x bar 3 plus x bar 4 plus x bar 5 all the way up to x bar n. And I'm going to divide by what? I'm going to divide by n to find the average, because you add up all the things and divide by how many you have. How many do we have? We have n of them. So I'm going to do add them all up, divide by n. When I do that, what I should get is the population mean. Now, again, I'm only going to get the population mean if the mean is what we call an unbiased estimator. So this will be true if the mean is an unbiased estimator. Now, mathematically, what that looks like is when we sum, right, x bar I from I equals 1 to n, and then we divide it by the number of samples we get. If the mean, or x bar, is an unbiased estimator, then when we find this, because all this is, don't get scared by the math, all this is taking the average. That's how we would mathematically, quote unquote, write taking the average. If we do that, take the average of all of our x bars, and we get the population mean, then guess what? The mean is an unbiased estimator. Now, unbiased estimators are really easy to work with because they give us almost the easiest way to estimate a population parameter. Because again, what is the goal of statistics? The goal of statistics is to discover parameters, right? That's what we want to do. We want to find out information about populations. Now, we have a couple of things that are unbiased estimators, right? The proportion is an unbiased estimator. The mean is an unbiased estimator. And the variance, right? Basically, what we mean is that those things target our population parameter, right? That's what they do. They target our population parameter, meaning when we work with them and we find the average, just like we did in this case, where we find the average value of the statistic, where we can put in whatever statistic is that we want here, we get the population parameter. So we find the average of all of the statistics that we found, right? All of the individual statistics, and what we get out, right, is the population parameter. Average all the statistics, get out the population parameter. Notice how I said that like 5 times? That's because that's really important. It's a really important note, a really important point. So these are all unbiased estimators, meaning that if we find the sampling distribution of the proportion and we average them all out, then we get the population proportion or something really close to it, right? So if we find the average of all of the sample proportions, we end up getting out the population proportion, right? If we find the average, right, of all of the sample means, we get out the population mean. And if we average, now for the variance is a little tricky, but it's the same kind of concept. Average of all of our variance, and this is again over the course of a sampling distribution, meaning we took every possible combination that we could for our sampling distribution, for our samples. We took every possible sample we could take out. So if we average it, we will get close or exactly to our population variance, right? So that's what an unbiased estimator is. It's like a really, really accurate dart where we're throwing the darts, and they all are equally the same distance away from the bullseye. So it makes it really, really easy for someone else to find out where the bullseye is. So there are, of course, since they're unbiased estimators, there are, of course, biased estimators, right? And biased estimators are basically ones that don't target the corresponding value of the population parameter, right? They don't target the population parameter. An example of that would be like the medians, the ranges, and the standard deviations, right? And basically what that means is if I average all of the medians, let's say I average all, so we took a whole bunch of samples and I average all of the medians of my samples, I will not end up getting the population median, right? That's not what I'm going to end up getting, population median. So there are other ways that we can do some estimates to get the population medians and stuff like that. But if I just average all of the medians, I'm not going to end up with the population median, right? The same thing for the ranges. If I average all of my ranges, I'm not going to end up with the population range, right? And with the standard deviation, if I just find the average of all of my standard deviations, I won't end up with the population standard deviation. Now, that's an important note because that's basically tells us what things we can kind of more easily work with and what things we can't. If we are doing the proportions, the means, and the variances, right, then we can more easily work to find the population parameters. It's actually a very simple process. Now, if we are working with the median, the ranges, and the standard deviations, there are ways that we can do it. It's just much more involved. So what we're going to start working with, we're going to start off working with the unbiased estimators. Now, when we are making a sampling distribution, right, or when we're just sampling and trying to take a whole bunch of different samples, right, we want to make sure that we are sampling with replacement. And there are two reasons why we want to make sure we want to sample with replacement. So one, if we're taking a small sample from a large population, then it doesn't really make a difference if we do it with replacement or not replacement, right? And a part of the reason is just that if you're taking 20 people out of a population of 300 million people, right? If your sample is random, it's not really going to make a difference, right? And the second thing is like what we talked about with the cards. We want to sample with replacement because then our events will be independent, right? Each time we take our sample, it will be independent. Remember we talked about it when we said if we do a prize for whoever picks the ace, right? The person who picks last, if no one else has picked an ace, the person who picks last, right, has a larger chance of picking the ace. Why? Because the first person is picking out of how many cards? 52 cards. The second person is picking out of how many cards? 51 cards. If we don't sample with replacement. The third person only picks out of 50. The fourth person out of 49, so on and so forth, right? So when we don't sample with replacement, what we end up is with a situation where the odds are unfair for each person, where each person doesn't have the same odds of being picked. And we want all of our sampling to be independent. That's what we want. So that's why we want to sample with replacement. Now they also say, which is another little note, that it makes it a little easier to analyze and gives us slightly different or simpler calculations when we sample with replacement, because it's just a little easier to work with independent events than to work with dependent events. Now, the central limit theorem, what we're going to introduce now, is one part of what we call the central limit theorem. Right? Now, it may seem like some mumbo jumbo a bit, right? But for this one part of the central limit theorem, when we do an example here, I think it'll make a little more sense. There are a couple more other parts of the central limit theorem, and we're going to introduce them kind of piecemeal like this so that you can kind of wrap your head around this part, and then we'll introduce another part next week. right? But the central limit theorem is important because it kind of lets us work with sampling distributions, right? That's what the central limit theorem lets us do. It lets us work with sampling distributions. It lets us deal with them and basically have a way to kind of go from the sampling distribution to our population values. So I'm going to read it out first, right? Just read it out. So for all samples of sample size n, where n is less than 30, right? The sampling distribution, right, of the mean x bar can be approximated by a normal distribution with a mean of mu and a standard deviation of sigma over the square root of n, right? So basically, what we're saying here is that if we are taking samples where the samples are bigger than 30, I think I said less than 30 when I read it out loud. I meant to say bigger than 30. So when we're taking a bunch of different samples where the sample sizes are bigger than 30, then we don't need to take so many different samples. Because remember, we said when we do a sampling distribution, right? When we do a sampling distribution, it's going to be a lot of samples that we need to take, and we may not have the ability to take all of those different samples. And also, if you're taking a sampling distribution, you might as well just do a census, because when you do a sampling distribution, you have to go to each and every member of a given population. So basically, what this is saying is that we can approximate the sampling distribution of the mean. So we can approximate the sampling distribution. Let me write this out. Distribution of the mean. That's x bar, right? We can approximate that as a normal distribution with a mean of mu and a standard deviation of sigma over the square root of n, right? That's what we're approximating our our sampling distribution as, right? So we're approximating it as this thing here. Now, it may seem like, okay, professor, why is that important? Why does that help us? That doesn't seem useful at all. But we'll see in a second why this is so useful. Now, another note that I want to just make really quickly. A lot of times what we'll call the standard deviation. So we'll call the standard deviation. A lot of times we'll call it the standard error. So we'll call it the standard error. So that's just a quick note, right? Because again, what's the standard deviation telling us? Right? Standard, there we go. I didn't spell that wrong. So the standard deviation is again telling us how far things are away from the mean on average, right? So that's basically telling us like the error, because everything should, quote unquote, should be at the mean, right? And the standard deviation is telling us like how far away we are actually from the mean, right? So it's almost like the error. That's basically what the standard deviation is. It's like the error, or basically how far things are on average away from the mean. Or if you think about our dartboard example, the standard deviation is basically how far on average each of our darts is away from the bullseye. And in particular, we call this standard deviation the standard error of the mean. Right? That's what we call this standard deviation. But we'll come back to that a little later. Right? But I just want to introduce that idea that we're going to call it the standard error in a little bit. Now, looking at the central limit theorem, where we're particularly talking about sample statistics, the sample means, right? Basically what we're looking at is we're saying that if we have any, and this is again one of the reasons why the central limit theorem is so important, because look, if we have any distribution, right? If we look back at our central limit theorem, the central limit theorem did not specify what kind of distribution the initial population had to have, right? It didn't say, oh, it needs to be skewed, it needs to be uniform, it needs to be normal. All it said was that if we have samples of the same size and the samples are bigger than 30, then we can do this approximation. Again, it's just two requirements. Samples of the same size that are bigger than 30, right? Then we can do this approximation. So that's what makes it so powerful, because it works with any distribution. Previously, we had just worked with normal distributions. Now, when we have normal distributions, there's special things that we can do. But when we have other distributions, we kind of have to fall back on the central limit theorem, right? So when we have a population that has a mean of mu and a standard deviation of sigma, right? Basically, what we're trying to do, is we're trying to find simple random samples, right, of the same size from that population. And we're trying to work with the sampling distribution that we create. And again, what we can do is approximate it as a normal distribution. So we're taking another distribution and we're approximating it as a what? A normal distribution. Now, here are the requirements for the central limit theorem to hold. First, our population has to either have a normal distribution already, or our sample sizes have to be bigger than 30. So let's say, for example, let's look at an example really quickly. What if our initial population was a skewed distribution? So it's not normal, it's skewed. And our sample size is 5. Would that work? Think about it for a second. Okay. No, we couldn't use the central limit theorem for this example. Why? Well, it's not a normal distribution already. Our population is not a normal distribution, and our sample size is too small. Let's do another example here. What if we had a normal distribution and our sample size was 15? Would this work? So just pause it for a second. Think about it. Think about those. Look at those requirements. There were two requirements, and it's an or. So it had to be one thing or the other thing. So think about it for a second. So when we look at it, we can see that this would work. Why? So although our sample size is not bigger than 30, we meet the first requirement. Our population had a normal distribution already. So yes, this one would work. Let's do one more. What if we had a uniform distribution and our sample size was 50? Would this work? So if we do this one and our sample size is 50, right? Well, it's not a normal distribution, but when we look at it, look at our sample size. Our sample size is 50, so this will work because either we needed to be a normal distribution or we needed a sample size bigger than 30. So we met one requirement here. Here we met this requirement, but here we met none of the requirements. That's why that one didn't work. So again, one of these two requirements, this is one, either it needs to be normal or our sample size, which is n, has to be greater than 30, right? That's what our sample size has to be. It has to be greater than 30. Hold on one second, you all. Now, moving on, when we find basically the mean of all of our sample means, right? The mean, this is what this is, the mean of all the sample means, that is going to equal mu, right? And the standard deviation of all of our sample means is a little different. When we find the standard deviation of all of our sample means, what we do is this transformation, right? Where basically we take the standard deviation and we divide it by the square root of n, where n is what? What do we say n was? N is the sample size, right? That's what n is. N is the sample size. Now, when we do our z-scores for these, right? And this part is kind of important. When we do our z-scores for these, we have to use, I'm going to erase this stuff down here, or a little bit of it. We have to make sure that when we do our z-scores, we are using the right values. So when we do our z-scores, instead of using the value itself, let me actually erase all of this. Right? So instead of doing the value itself, when we do our z-score, so originally what we had was z equals x minus x bar over the standard deviation, where this was the value we were trying to find the z-score of. This was the mean, and this was the standard, right, deviation. Now, when we are doing this here, we're doing something a little different. So when we do this here, what we're doing is we're finding the z-score for one of the sample means. So this is the z-score for a sample mean. So let me write that, z-score, right, for one of the means. So let's say we want to see some probabilities or something. This is what we would be doing. So z-score for a sample mean, what we're doing here, instead of doing the value, right? Let me write it all out and then I'll draw some arrows and tell you what each one is. Sigma over square root of n, right? Instead of doing that, what we're doing here, this is a mean. So we're trying to find the z-score of a mean, right? So the mean of a population. So this is a mean, a statistic mean, a sample mean. That's a sample mean. This mu is the population mean. That's what mu is the population mean. And then here is our standard deviation transformation, where basically we have the standard deviation. And what are we dividing it by? We're dividing the standard deviation by the square root. SQRT is square root of the sample size. The sample size again is n. So that's what we're doing here. Now it's a little different because here we're finding the z-score of a mean, right? And we're gonna do an example again in a second where we kind of see what we're talking about. But we're finding the z-score of a mean. Now, excuse me. So if we have a situation, right, where if we have a situation where our original population is not normally distributed and, right, our sample size is less than 30, then guess what? We can't do any of the stuff that we're talking about here. None of the stuff we're talking about here applies. So you need to make sure that you need to just do a check, do a mental check. Is our original population normally distributed, or is, our sample size bigger than 30? So that's what we're doing. We just need to do a check, right? Is our thing an original thing, or is it a normal distribution originally, or is our sample size bigger than 30? So either one has to be true. Right? And if we can't do it, then we cannot do any of this stuff. We can't use the central limit theorem to apply it. So the first thing we want to do, step one, when we're doing one of these problems, step one is we want to check the requirements, right? So when you check the requirement, first you need to start off and say, am I working with a normal distribution? Is the population normally distributed? If the population is not normally distributed, then you need to say, is my sample size bigger than 30? And let's say you have a sample size, let's say you don't know if the population is normally distributed, right? Then as a check, what you should do is you should just pick a sample size bigger than 30. Do a sample size that's bigger than 30, right? The second thing we need to do is we need to ask ourselves, are we trying to find information about a single value or about a mean? Right? And we already kind of talked about this, because when we're trying to work with a single value, this is what we use for our z-score. Right? We're talking about a single value. So let's say you're trying to find the z-score of an individual person's height in our class. Right? That's what you would do. You would do this here. So this would be like the z-score of an individual person in our class. Hold on. That's what that would be. The z-score of one person's height. Now, I know we always come back to a height thing, but it's just really easy to work with. So that would be the z-score of one person's height. That would be like an individual value. And if we were doing a mean, then we would do this one. And this would be like the z-score of our class's height, right? The z-score of our class's average height or mean height. The whole class, meaning we just took the whole class. Let's see, I'm having my spelling problems. Hold on. Because that should instead be the z-score of our class's mean height, right? And basically, we'd be comparing our class's mean height with another class's or with everyone else, every other class, right? So we would need to find the z-score of our class's mean height. So this is step two. Are we dealing with an individual value or are we dealing with the mean, right? So if we were talking about our class's mean height, then we do this. Now again, make sure you remember this. Sigma over the square root of n. That's important. That's what you use as our standard deviation, right? Sigma over the square root of n. That's very important. Now, moving on. So continuing, and again, we're looking at practical uses of the central limit theorem. That's what one practical use, at least, of the central limit theorem, right? Now, what we want to do here is we just want to talk about kind of how we're noting things. Now, again, this is what I was telling you all. We call that the standard error of the mean. So that's what this is. This is the standard error of the mean, or the SEM. So if you need to find the standard error of the mean, that's what we find. So if we're dealing with means, we use this, the standard error of the mean. That's what we use, right? And again, mu, that's the mean of all of our x bars, right? That's what that is, the mean of all of our x bars. So it's the average of all sample means. Right, that's what that is, the average of all sample means. So let's look at this example here, right? So this example, we're looking at an elevator loading. We want to try to load our elevator in a safe manner, right? That's what we're looking at here. Now, when you read the sign on whatever elevator this is, I don't know what elevator this is, but when you read the sign of whatever elevator this is, The elevator says it has a capacity, right, of 27 passengers. That's what the elevator says. It's a capacity of 27 passengers. So the question is, right, if we know on average how much each passenger weighs, right? So if we have 27 passengers, we can say, okay, well, if the elevator was full, right? The full elevator and couldn't take anyone else. Uh-oh. Let me erase this. If we had a full elevator of the 4,000 pounds, we could divide it and say that each person could be what? Could be at most 148 pounds. Or at least the people would need to balance out to have a mean weight of 148 pounds. So again, let's just look at what we know so far. The elevator can support a maximum of 4,000 pounds or 27 passengers. And when we do the division, that tells us that each passenger has to have, basically the elevator has to have an average weight of 148 pounds per passenger if there were 27 people in there. And again, all you did was just divide the total amount by the 27 to get that 148 pounds. Now, the worst case scenario for this elevator, if we assume that the worst case scenario is that the elevator is full with 27 adult males, right? And we can also assume, because whatever research we've done research, we can assume that adult males have weights that are normally distributed, keyword, with a mean of 189 pounds and a standard deviation of 39 pounds, right? So adult males look like this. This is what adult males look like. Let me erase that really quickly. Hold on. I need to make it a little smaller. So this is what adult males look like. They have a mean weight of what? 189 pounds. And a standard deviation of what? 39 pounds. The N tells us it's a normal distribution. Then first we put the mean, then we put the standard deviation. So that's adult males. This is the weights. That's what this is. Weights of adult males. Now the two questions this is asking us. The first question is saying, find the probability that one randomly selected adult male has a weight greater than 148 pounds. So that's the first question. Find the probability that one randomly selected adult male has a weight greater than, right? A weight greater than 148 pounds, right? And then question 2 is saying, find the probability that a sample of 27 randomly selected adult males has a mean weight greater than 148 pounds. So one part is telling us, let's just look at a single adult male, while the other part is telling us, let's look at a sample of 27 randomly selected adult males. So what I want you to do here is I want you to pause the video. And while you pause the video, I'm going to put a new page in here. But I want you to pause the video, and I want you to try to see if you can solve this problem yourself. At the very least, you should be able to solve part A using the information we did last week, right? Remember, we had like a couple of steps. So you should be able to solve part A using the chart and the information that we did last week. So let me open this up. Let me do a new slide really quickly. Hold on. Insert. So you pause the video. You should be working on it now. Pause the video and then continue. I'm going to add a couple of these. And if we don't use them all, that's okay. All right. So let's look at the first one. So you can resume it. We're going to do the answer now. So let's look at the first one, right? So part A, right? What's part A say? Find the probability that one randomly selected adult male has a mean weight greater than 148 pounds. So first, so this is part A. First, let's say, what are we working with? We're working with a normal distribution, right? With a mean of 189 and a standard deviation of 39. That's what we're working with here. Now, what we want to be able to do is we want to find the probability that one person that we pick at random has a weight greater than 148 pounds. Now, because this is a normal distribution, we can do everything that we did last class. In last class, what did we say we need to do? Well, step one, right, was to what? Draw the picture. So let's draw the picture. Don't get on me for my picture being ugly. Step one is draw the picture. Now, this is I'm going to just draw it over here, just in case. It's not drawing the scale. This is a normal distribution. Now, what goes in the middle? In the middle, we put the mean. The mean is 189 pounds. Now, in this case, what we are doing is we are starting with a value, right? We're going to go and convert our values into z-scores. That process is standardizing it. And then we're going to use that to find probabilities. So we're starting off with 189 pounds. Now we're trying to find the probability that one person has a weight greater than what? 148 pounds. So we want to find, let's just write it there. Hold on, let me erase this really quickly. I don't know. Sometimes it's like my pencil's trying to just come out too thick. Technical difficulties. So we're trying to find the probability that one person's weight, one adult male's weight, is greater than 148 pounds, right? That's what we're going to find. Probability that one adult male's weight is greater than 148 pounds. So when we do this, what do we need to do? Well, we need to draw a picture. We need to label it. So if this is 189 pounds in the middle, 148 pounds would be like, we'll just assume it's like right here. Now we're dealing with what? Greater than, so let's draw a line up. And which side is it that we care about? Well, we're doing greater than 148 pounds. So which side is it that we care about? This side over here, right? This is the side that we care about over here, since we're dealing with greater than 148 pounds. So what do we need to do? Well, we need to go to our chart. And when we go to our chart, we need to find the probability based on our chart. We need to use the chart to find the probabilities. But before we do that, we need to do our z-score conversion and standardize it. So let's standardize it. So to standardize it, what do we use? We use z equals, I don't know why it keeps doing that. We use z equals, again, because we're doing an individual person, not a sample, an individual person. We do z equals the value minus the mean divided by the standard deviation. That's what we do. So to do that, what do we have? What's the value? The value is 148. The mean is minus 189 divided by the standard deviation, which is 39. So, right, we do the value minus the mean divided by the standard deviation, and we end up getting negative 1.05. That's what we get, negative 1.05. Now, what we're going to do here is I'm going to go here and go to the z-score table, because now we know our, let's type in z-score. Let's percentage z-score. I can't remember what the website is that I told you all to go to before. It's like ztable.com. There we go. So ztable.com. So now we're on ztable.com. And when we go to ztable.com, what z-score are we looking for? We are looking for negative 1.05. Let me write that. So 189 is the mean, so it has a z-score of 0. This has a mean z-score of negative 1.05. And when I look at that one on my z-table, where am I looking? Where do we see? Negative 1.05. So I'm right here. If I go down in the z, I'm right here, 1.0. And I go over 1.05. And I get 0.1469. So let me actually, I get, I'll zoom out a little bit, negative 1.05. That's all the way down at the bottom. And I get 0.1469. That's what I get, 0.1469. What I'm going to do really quickly is I'm going to connect this thing so that you all can see it where I'm looking at. Give me 1 second. Give me 1 second. Technical difficulty. So I want you all to be able to see exactly how I found that probability. Okay, I'm just gonna say technical difficulty. I won't be able to show you how I found it, but you got to go down on the first column, that Z column. Go down on the Z column. You know what I can do? I can take a screenshot. I think I can do that. I'll take a screenshot. There we go. So I took a screenshot. So now what we'll do, don't laugh at me and say I'm old. So what I'm doing is I'm going down on this Z column and I go to negative 1.0. And then I go over up until I get to, so I'm going over here. And I want to go over until I get to the 0.05 column. And that point, that's where they intersect. That is the answer that I'm looking for right there for my probability. So what probability I get? 0.1469. That's what I get. 0.1469. Yeah, we'll save it. 0.1469. So let's go back to our slides. And we get 0.1469 as our probability. But remember, everything on the table tells us what is to the left. So this is this value over here. So what do we need to do? To find this value over here, we need to do 1 minus it. So we do 1 minus 0.1469. And what do we get? We get 0.8531. So that's what we get. So the probability that someone is above it is that 85.31%. Now again, this is for what? An individual person, right? That's what this is for. It's for an individual person. And that's what we end up with. Probability of 85.31%. Now, the second question, what did the second question ask us? Find the probability that a sample of 27, keyword 27, randomly selected adult males has a mean weight greater than 148 pounds. Now, guess what? We're going to do this almost exactly the same way. So we're going to start off, what are we working with? We're working with a normal distribution, and our mean is 189. Our standard deviation is 39. So that's what we're starting off working with. Now, because here what we want to use is we want to look at samples, right? We want to look at sample means and not individual values. This tells us that we want to use the central limit theorem. So we want to use the central limit theorem. And in order to use the central limit theorem, we have two conditions, right? Or it's an or condition. So either one or the other. So either our sample size needs to be bigger than 30, or the population needs to be normally distributed. So if we look at our question, what's our sample size? Find the probability that a sample of 27 randomly selected adult males. Now, is our sample size bigger than 30? No. What does n equal here? N equals 27. So our sample size is not bigger than 30, but what was the second condition, right? Either it needed to be normal or n greater than 30. So n is not greater than 30, so we're going to cross that out. That didn't work. Is it normal? Well, yes. We already said that our original population of adult males is normally distributed. So then, yes, we can do this, right? And when we do this, what we can do here is we can approximate, because that's what we're going to work with. I zoomed in. What we're going to do is we're going to work with the sampling distribution. Right? We're going to work with the sampling distribution. And since we're working with the sampling distribution of means, right? What we need to do is we need to do the approximation. And the approximation tells us that we can approximate this as this, a normal distribution. Our mean doesn't change. The only thing that changed was the standard deviation. So our mean is the same, and our new standard deviation is going to be what? Our new standard deviation, sigma x, equals sigma over the square root of n, right? That's what our new standard deviation equals. So what that's going to be, that's going to equal 39, which is our old standard deviation, divided by the square root of what? 27, because that's our new standard deviation. What do we get when we do 29 divided by the square root? So I need to put it down here probably. I won't have space. 39 divided by the square root of 27 equals 7.51. So this is the new value that we're working with for standard deviation, 7.51. Right? That's our new value for our standard deviation. Now, what we're going to do here, right? What we're going to do here is we're going to do basically the exact same thing. Right? Now, when you do a problem, you don't have to write out all of this stuff. The only thing you need to write is basically this part. This is the only thing you would need to write of what I wrote so far. You need to write this part and write that part. And that, again, is our approximation that the central limit theorem lets us do. So what do we start with? We're going to start with the exact same thing. We're going to draw a picture. And after we draw a picture, what goes in the middle? 189 goes in the middle. What are we going to put here? We're going to put the value that we're looking for. We're trying to find out what's the probability that the mean of our sample, x bar, is greater than 148. So we're going to put the 148 here. And again, we're dealing with greater than. Greater than tells us that we're dealing with stuff over to this side over here, right? To the right. Now, because we're dealing with greater than And that stuff to the right, what's next? So we draw a picture. What's next? Next, we need to standardize it. That's going to be 0. For this one, the 148, we need to find the z-score of it. Now, to find the z-score, this is where things get a little different. Instead of using this value, the original value for our standard deviation, we need to instead use this new value for our standard deviation. So what we're going to do is z equals x bar, where x bar is the mean that we care about. Because again, we're saying what's the probability that this group of 27 people has a mean greater than a certain value. So that's z equals x bar, right? Minus what? The population mean, mu, divided by this new value over here. I went back. This new value over here. Sigma over the square root of n. That is the difference. When we're dealing with a mean, when we're trying to find the probability that a sample has a mean bigger or smaller than a certain value, this is what we use. We use the central limit theorem, and we use this transformation for our z-score. Now, when we do that, plug in the numbers. What is x bar? Well, we're trying to find the probability that they have a mean over what? 148. What's mu? Mu is the same. It didn't change. 189 divided by, we already did this part, didn't we? That's this. We already did this part. That's this up here. And what do we get? 7.51. So now we can find that z-score. And when we find that z-score, what do we get out for that z-score? We get out, when we calculate this, put in your calculators, we get out negative 5.46. See how different our z-score is? When we did the z-score for the individual person, we got negative 1.05. But when we did the z-score for the sample, a group of 27 people, we got negative 5.46, right? And the reason is that when you get a larger and larger group of people, our mean should be closer and closer to the population mean, right? And that's the idea, that the mean should be closer and closer. That's why this, for when we look at it for a whole population, that's why it's so much more extreme, because it should be closer. It should be closer. So we got negative 5.46. Let's write that, negative 5.46, right? And when we have that there, that's our z-score. If we go back to the chart, it's going to be an uh-oh moment, because look at the chart. The chart stops where? Negative 3.4. There's nothing bigger than negative 3.4. So what we're going to put for this case, right? For in this case, what we're going to put that this has a probability of 0.0001, which is like super small. So you can go back here. You can see that the smallest one they have here is 0.0002. Anything past negative 3.49, we're just going to put 0.0001. That's what we're going to put for anything past 0.3.49, 0.0001. Now, for that 0.0001, again, what is this probability? Probability we end up over here. But we wanted the probability that we end up on that side. So what do we need to do? 1 minus 0.0001. And what do we get? We get 0.9999. So when we look at that, that tells us that there's a 99.99% chance, right? 99.99% chance that our group of 27 adult males is going to have a mean weight bigger than 148 pounds, right? And basically what that tells us, when we look back at our elevator example, that basically means that our elevator is going to fail, right? Our elevator is going to fail because it's 99% chance, 99% chance that it has a mean weight bigger, that the group, right, has a mean weight bigger than 148 pounds. So I just want a quick little recap of the example that we just did. Quick little recap. So first, when we do an individual, right? Everything is the same. Same steps. Everything is the same. Right? And our z-score is z equals x minus x bar divided by standard deviation. But when we're looking at a group or a sample, right, things change. Here, instead, our z-score is different. The whole process is the same. The process doesn't really change, right? The only difference is we use a different z-score. Our z-score is now going to be x bar minus population mean divided by standard deviation over the square root of n. That is our new thing, where n, right, n equals the sample size. That's what we get. And now, again, another note, it's going to be important in a little bit. Square root, sigma over the square root of n, another name for that is the standard error of the mean, right? That's another name for that. Now, the next couple of slides are just in the slides it worked out so that you can go back here. And basically, this is just a little summary. We already kind of looked at this already, right? We looked at our two probabilities, but that's just working out the problem. Right now, we're going to discuss this next week in class. We're going to discuss all of this next week in class, but you should still go through it. There will be some practice problems, some example problems, but you should still go through all of this. You should still go through it. Again, pause the video, try to work through it, try to see if you can figure out what the next step is, etc. So if that, we are done, and I will see you all in class. Don't forget, you can email me, you can call my office phone number, or you can email me if you have any questions. All right, have a good night, everyone.